All right, welcome to section 2.2. In this section, and for a large part of the remainder of this chapter, we're going to be talking a lot about computing volumes now. So previously we were talking a lot about areas and how to compute areas of two-dimensional regions, and now we're going to increase the dimension by one and start thinking about how to compute volumes of three-dimensional regions. Before we do this, we're going to need to make an assumption similar to how we made an assumption at the very beginning of the course. At the beginning of the course, we talked a lot about how the volume or the area of a rectangle was its base times its height, and we need to make a similar assumption here in order to make any progress towards computing volumes of anything at all. So before we go on and talk about the right assumption to make, what we need to do is we need to have a couple more words, of course. So we're going to start with a definition. Given a plane region R, meaning that R lies in a plane, and that is exactly to say that R is a two-dimensional shape. So given this region R and some positive real number h, the cylinder with base R and height h is the three-dimensional solid generated by translating R along a line perpendicular to the plane in which R lies. So what exactly does this mean? It's maybe most helpful to illustrate this with an example. So if I let R, for instance, be some pentagon, then R here is certainly a plane region. Because, well, the pentagon lies in a plane, and namely it's the plane that is formed by the, I suppose, computer screen that I'm writing on. So R here is some plane region, and what we can do is we can form the cylinder with base R and height h by translating R along a line perpendicular to the plane. So if we think about what line might be perpendicular to the plane of my computer screen, it would be the line that comes straight out of the computer screen towards my face. So what I would like to do then is I would like to take this region R here, this pentagon that I've drawn, and translate it out of the page. I would like to pull it straight out of the page. And in doing so, this is going to form some three-dimensional solid. In particular, if I were to draw it, I would get a pentagonal prism that would look something like this. So I'd have the face here, and then it would go back here, and I would have some kind of pentagonal prism. So the solid that I get here is called a cylinder, which you'll notice is a little bit different than how we're used to using the phrase cylinder. However, if we started maybe with the plane region R equal to a circle, then what we would get by translating this circle out of the page is the thing that we're used to calling a cylinder, namely we would get the cylinder with kind of a circular base. So in any case, we are using this cylinder a little bit more generally because we are in fact calling both of these things cylinders. What does h mean? Well, h means the distance that we translated it. So in this case, it's going to be the difference from the distance between one face to the other. So what's this assumption that we're going to be making? Well, we're going to be making the assumption that for a cylinder, or rather that, maybe let's rephrase this. A cylinder with base area R, or maybe base area A, and height h has volume A times h. In other words, when we take a cylinder, we're just going to take the area of its base, and the area of its base is rather a two-dimensional region by the definition of what a cylinder is. And so two-dimensional regions are something that we are now experts at finding areas of. We spent some time in Chapter 1 and in Chapter 2.1 really looking at how to compute areas of various two-dimensional regions. Now that we're really good at that, what we're saying is if we can find the area of the base of the cylinder, and we know how far out of the page we've pulled the cylinder, then we can find the volume of the cylinder simply by multiplying the area by the height. Now, what I want to kind of point out here is that this is very similar to the analogy that we made, or this is very similar to the assumption that we made at the beginning of Chapter 1 when we were talking about the area of a rectangle. There's kind of an analogy here, which is that if we, for instance, know, so let's start with the assumption that we can call this the size of an interval a comma b should be b minus a. In other words, this is kind of the length of the interval. So what we did when we were looking at the area of a rectangle, we said, well, what we're doing to create a rectangle is we're taking this interval AB and we're going to translate it along a line perpendicular to the shape AB. And translate along line perpendicular to AB. So here's my interval AB, and I took this interval and I translated it along a line perpendicular to it. So for instance, that direction is this way, and I created some rectangle with height h. And the assumption that I made about the area of this rectangle was that the area is equal to the size of AB this is the base of the rectangle times h. So this new assumption that I'm making is very similar to the one that we did previously, in the sense that now I'm starting with some two-dimensional region. I'm translating it along a line perpendicular. I'm getting this thing that I'm calling a cylinder. And I'm taking the size of this new cylinder that I've created to be the size of the lower dimensional thing, the two-dimensional region, and multiplying it by the height that I'm translating it by. So hopefully this seems like the right kind of assumption to be making about volumes here, and that it's very analogous to the assumption that we made about the volume of a rectangle, for instance. All right, so we'll leave it here for now that we've got this new notion of a cylinder and we have the notion of its volume, and in the next video we'll start to talk about how we can compute volumes of shapes that aren't